Welcome to this explainer. Okay, let's just jump right into this mystery. Imagine a massive fortune of ratinas, precious stones, just locked away, completely out of reach, waiting for someone clever enough to claim them. This was the brilliant setup left behind by Queen Ratnamanjari. She really wanted to leave her entire inheritance to her son, Koisnam, but she knew that their 99 relatives would endlessly pester him if she just handed it over on a silver platter. So she designed this incredibly clever mathematical puzzle to test him, and she wrote it right into her will. So here's the deal. The stakes? Literally as high as they get. The Queen's note explicitly stated that if all 100 relatives solved it together, they'd have to share the ratinas equally. But, and this is a big but, if one person solved it first, they got the entire fortune all to themselves. So the Queen's minister gathers Koisnam and the 99 relatives in a secret room deep inside the mansion. And lining the walls of this room, exactly 100 closed lockers. All right, the minister then lays out the ground rules, and it's basically like a giant moving puzzle. Each person gets assigned a number from 1 to 100. Person 1 walks down the line and just opens every single locker. Person 2 follows, but they only toggle every second locker, so closing it if it's open or opening it if it's closed. Person 3 toggles every third locker, person 4 toggles every fourth, and this whole routine continues all the way until the 100th person takes their turn. The open lockers at the very end will reveal the code to the safe. Now, before a single locker was even touched, Koisnam just smiled. He already knew exactly which lockers would be standing open at the end of the 100 turns. The question is, do you? Take a second, really think about it. It sounds super chaotic, right? People just opening and closing doors in these overlapping patterns. How could you possibly predict the end result without physically walking through all 100 steps yourself? Well, the secret lies in looking at exactly how many times a single locker gets touched. Let's zoom in and look really closely at just one locker. Locker number 6. Who actually touches it? Well, person 1 opens it, person 2 closes it, person 3 opens it, and finally, person 6 closes it. The people who touch locker 6 correspond exactly to the mathematical factors of the number 6, 1, 2, 3, and 6. Because there are exactly 4 factors, the locker is toggled an even number of times. Open, closed, open, closed. It ends up completely shut tight. Now, while he was running the math in his head, Koisnam actually spotted this cool little Easter egg hidden inside the puzzle. He noticed a clue about a smaller passcode made of the first 5 lockers touched exactly twice. So which lockers are only touched twice? Well, the ones with exactly 2 factors, 1 and themselves. We call these prime numbers. By uncovering this secret, he found the first 5 prime lockers, 2, 3, 5, 7, and 11. But that still doesn't tell us which lockers stay open at the very end of the whole process. Okay, so here's the absolute game changer. It's all about parity. If a locker has an even number of factors, it's going to end up closed. If it has an odd number of factors, it stays open. But if you think about it, factors basically always travel in pairs. Take the number 12, right? You have 1 times 12, 2 times 6, and 3 times 4. They pair up so neatly. And because they come in pairs, the total number of factors is almost always an even number, which means almost all of the 100 lockers are going to end up closed. But wait, is there a time when a number doesn't have an even number of factors? Is there an exception? Let's look at the number 36. It has the pairs 1 and 36, 2 and 18, 3 and 12, 4 and 9. And then boom, we hit 6 times 6. Both numbers in that pair are exactly the same. And you obviously don't count the number 6 twice when you're listing factors. So the unique factors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, and 36. Count them up, and that is 9 factors, an odd number. So locker 36 is going to remain open. This right here brilliantly illustrates the whole concept of square numbers. A number that can be expressed as the product of a number with itself is a perfect square. And it's not just some abstract math idea. It translates directly to the physical world around us. If you build a square shape with little building blocks, a side length of 3 gives you a total area of 9 square units. Or say you know the area of a square piece of cloth, like a handkerchief, is 25 square inches. You immediately know each side has to be exactly 5 inches long. Perfect squares literally bridge the gap between abstract numbers and physical space, and they are the only numbers in existence that have an odd number of factors. So armed with this profound mathematical truth, Koisnam knew exactly which lockers would be standing wide open when that 100th person finished. The perfect squares. In his head, he mentally listed the square numbers from 1 to 25. So that's 1, 4, 9, 16, 25, and he just kept going. 36, 49, 64, 81, and finally 100. By understanding the true nature of factors and perfect squares, he secured the entire fortune of Ratna's without lifting a single finger.
Now, let's step beyond the mansion for a second and see how this builds into these incredible mathematical patterns you can spot everywhere in life. If you write out the first 30 perfect squares, you'll start to notice something super peculiar about their units digits, the very last number. They always end in a 0, 1, 4, 5, 6, or 9. They literally never, ever end in 2, 3, 7, or 8. Now sure, if a number ends in a 6, like 26, it isn't automatically a square. But if a number ends in a 7, you can instantly, confidently say, nope, absolutely not a perfect square.
And what about zeros? There is a fantastic math life hack right here. Just look at the number of zeros at the end of a number and compare it to the zeros at the end of its square. If your original number has 1 0, like 10, the square has 2 zeros, like 100. If your number has 3 zeros, its square will have exactly 6 zeros. The number of zeros at the end of a perfect square is always double the number of zeros of the original number. So perfect squares can only ever have an even number of trailing zeros. We can also look at parity, which is just a fancy way of saying whether a number is even or odd. The rule here is beautifully simple and incredibly fast. The square of an even number is always going to be an even number, like 4 squared is 16. And the square of an odd number will always, without fail, be an odd number. 5 squared is 25. The number and its square are permanently linked by their parity. But honestly, this next part might be the most beautiful pattern of the whole shebang. How perfect squares relate to odd numbers. If you take consecutive odd numbers starting right from 1 and add them up, you literally generate the sequence of perfect squares. Think about it. 1 equals 1 squared. Add the next odd number, 3. 1 plus 3 is 4, which is 2 squared. Add the next one, 5. 1 plus 3 plus 5 is 9, which is 3 squared. Adding the first n consecutive odd numbers perfectly produces n squared. It's like magic, but it's just math. And get this. You can actually use this trick to calculate massive squares entirely in your head. Let's say you already know that 35 squared is 1225, but you really need to know what 36 squared is. Well, you know that 1225 is just the sum of the first 35 odd numbers. So to get 36 squared, you just need to add the 36th odd number. The formula for finding the nth odd number is simply 2n minus 1. So 2 times 36 minus 1 gives us 71. Add that 71 to 1225 and boom, 1296. You just found 36 squared using nothing but simple addition. And of course, a golden rule in math is that if a trick works forwards, it works backwards. We can actually use this odd number rule to find a square root. Let's take the number 81. We just successively subtract consecutive odd numbers, starting from 1. 81 minus 1 is 80. 80 minus 3 is 77. If you keep doing this, you hit exactly 0 on your 9th subtraction step. So, the square root of 81 is 9. But what if you're trying to estimate something huge in real life? Say you've got a massive square plot of land that's 8,000 square meters. You know that 90 squared is 8,100. So instead of doing subtraction all day long, you can instantly estimate that the boundary length of your land is just a tiny bit under 90 meters. And you never even had to touch a calculator. And the visual connections, they don't stop there. Perfect squares also have this fascinating relationship with triangular numbers. Those are numbers that can form a dot pattern of an equilateral triangle, like 1, 3, 6, 10. If you visualize it, watch how the dots of two triangles slot perfectly together. If you take literally any two consecutive triangular numbers and add them together, they magically form a perfect square. It is absolutely incredible how these shapes and numbers weave together in geometry and algebra. Now, we've been talking a lot about finding the square root, but there's a vital kind of technical detail we can't skip over. When we ask for the square root of 64, we usually just say 8 because, obviously, 8 times 8 is 64. But remember your negative numbers. Negative 8 times negative 8 is also positive 64. So technically, every perfect square actually has two integer square roots, one positive and one negative. For everyday geometry, we stick to the positive root, but that negative root is always hiding right there in the background of the math. Okay, time to put on my Quizmaster hat. Let's see how much you've picked up. I have 5 quick practice questions for you based on what we've learned. I'm going to give you 5 different numbers: 34, 46,
56, 74, and let's throw in 86 for good measure. If you squared each of these numbers, which of the resulting massive numbers would have the digit 6 in the final units place? Take a second to recall that units digits rule we talked about a minute ago.
Got a guess? The answer to all 5 questions is yes, every single one of them. You don't need to do any heavy multiplication here at all. Just look at the final digit of the original numbers. They all end in either a 4 or a 6. Since 4 times 4 is 16 and 6 times 6 is 36, any number ending in a 4 or a 6 will always produce a square that ends with a 6. Spotting patterns like this makes complex math incredibly fast and intuitive once you see the underlying structure.
All right, let's leave you with one final, slightly more abstract puzzle to chew on, pulled straight from our source material. Imagine P and Q are successive perfect square numbers. That just means they're right next to each other in the sequence, like 16 and 25. Is there a rule or a formula to figure out exactly how many non-square numbers lie trapped between them? Take a moment. Think about it.
Yep, there is a formula. If you take the larger square, Q, subtract the smaller square, P, and then subtract 1, you will always find the exact number of integers lying between them. So, for example, between 16 and 25, it's 25 minus 16, which is 9, minus 1 giving you 8 numbers. And let's check it. 17, 18, 19, 20, 21, 22, 23, 24. Exactly 8 numbers. It's just more proof that our numerical world isn't random at all. It's built on these elegant, deeply predictable rules. So the next time you look at the tiles on your kitchen floor or the grid of a city street, ask yourself, what other invisible mathematical laws are dictating the shape of the physical world right beneath your feet? Keep questioning and keep exploring. Thanks for joining me on This Explainer.